And just, you know, Jeff and I do answer.
All right, hello, good morning, everybody. This is Andreas Goetz speaking from the San Diego Supercomputing Center. And so welcome to the webinar. And I will talk today about GPU computing and programming and a little bit on how to get along for GPU computing on our supercomputer here at SDSC, so SDSC Comet. So if you have any questions during the webinar, you can use the chat, and we have Mary Thomas and Jeff Sale here who would be able to either answer some of the questions or maybe refer them to me so that I could answer questions that you might have along the way. The webinar is going to be approximately an hour. I'll try to stick with the time and we'll see how it goes and go from there. So let me see if I can advance the slides. Yeah. So the overview is basically what I will cover is going a little bit over GPU hardware overview, quickly talk about some GPU accelerated software examples, and then how to program GPUs using libraries that are GPU enabled, give a very, very quick introduction to PUDA-C programming, so what you have to know to understand a little bit what happens when you run a GPU code and how you could get started yourself. A short introduction to OpenACC, and give you a quick overview on how to access GPU nodes on Comet and run GPU jobs on SDSC Comet. So to go back, what is a GPU? It's basically, you might have heard the term accelerator, and an accelerator is simply a specialized hardware component that speeds up certain aspects of a computing workload. Some of you who are a little bit older, like myself, might remember floating point coprocessor, for instance, in older PCs that were specialized chips to perform floating point math in hardware rather than software, so that could speed up mathematical operations. More recently, there are also field programmable gate arrays, FPGAs, and of course, graphics processing units are very widely used and very popular. And a GPU is basically a specialist processor to accelerate the rendering of computer graphics. And that development has been driven by a very big gaming industry. There's a lot of money involved in there, which explains some of the developments that have happened over the last decade. Originally, that GPU hardware was using fixed function pipelines, so they were not easily programmable for general purpose. But nowadays, modern GPUs, basically since a decade approximately, are programmable for general purpose computation, so that you can effectively use them for any computing task that otherwise you would be using a central processing unit for. However, in comparison to a CPU, there's a simplified core design, if you want so. So with limited architectural features, for instance, branch caches, and there's a partially exposed memory hierarchy that you should know about when you're programming GPUs. And just to give you a background of why there's such an interest in GPUs, so on the right, you see a plot that plots the years and then a number of different properties of integrated chips. So what you can see is, for instance, in yellow, the number of transistors in thousands, and it's a logarithmic scale. That's basically Moore's law that you have probably heard about, which states that a transistor count approximately doubles approximately every 2 years. And that still holds nowadays, this exponential growth. However, since the mid-2000s, what you can see in black, for instance, the number of compute cores, we started to get like multi-core CPUs. And the reason is simply because the performance of a single processor thread, single processors being basically has been constant, and the single thread performance has not increased as dramatically as it used to. So while in the past you could just wait 2 years to double the execution performance of your code, that's not the case anymore. And since the mid-2000s, we must write parallel code. And why is there such an interest, particularly in GPUs? If you look at these plots, what they're plotting here is the floating point performance on the y-axis versus the year. And in blue, you see Intel Xeon CPUs. And in red and green, you see AMD GPUs and NVIDIA GPUs. And what you can see is that GPUs offer significantly higher floating point performance than CPUs. Again, so that's a logarithmic scale, and that gap has, so the GPUs have maintained that performance gap. It holds both for gaming GPUs and as well as data center GPUs. In particular, if you are interested or need 64-bit floating point for performance, you have to use so-called data center GPUs, which are more expensive than the cheap gaming GPUs. But that's not all. GPUs also have a significantly higher memory bandwidth than CPUs. So that's important because if you can't get the data from RAM to the processing cores, you're effectively wasting flops. So what we say nowadays is that flops are free. So and most codes and most algorithms are actually memory bandwidth bound. And also here, GPUs outperform CPUs in terms of the memory bandwidth. So in principle, a combination of the high memory bandwidth and the high floating point performance should lead to a higher performance of your code if it has been written in a proper way. So if you're using algorithms that can make use of the GPU architecture. Then again, if you look at the power consumption to have a fair comparison, so a single CPU current version on the right-hand side on that plot, you see that consumes approximately half the power of a single high-end GPU. So a fair comparison in terms of like performance given a certain power consumption would be a single GPU, for instance, a Tesla P100 versus two high-end CPUs in a dual socket CPU server. Now, here's a summary again, just to give you again an idea about comparison of CPUs versus GPUs. So we have a table here with a high-end dual socket Intel 8180 Skylake, so 28 core CPUs, that was 56 cores in total. And in such a server, you could stick in, for instance, two V100 NVIDIA Tesla GPUs. So these are the high-end data center GPUs by NVIDIA. And so you can see that the peak performance, and both in double precision and in single precision, is approximately a factor of 3.5 higher. This is now comparing two GPUs to the two CPUs. In addition, what GPUs have available in hardware now is so-called half precision. So if you have an algorithm, typically that's machine learning nowadays, you can get very high performance also with a 16-bit floating point numbers. And the memory bandwidth, of course, is also much higher. And then I have one row here that is the PCI Express bandwidth. So that's something that you don't have to worry about in a CPU, but since the GPUs, they are basically accelerators that are stuck in most of the cases into a PCI Express bus, you have to transfer data from the RAM that's attached to the CPU to the GPU through that PCI Express bus, and that has a relatively low bandwidth, so that can be a performance bottleneck. And code, is it portable? Yes or no? We'll learn a little bit more about that. In principle, also GPU code is portable if it's been written with OpenACC or OpenCL, not necessarily with CUDA, although NVIDIA is a very strong company, so it's probably not going to go away anytime soon either. Just as a historical perspective, if you look at the top left, so that's ASCII White supercomputer that was the #1 on the top 500 list in 2001, so almost 2 decades ago, in Lawrence Livermore National Lab, had a peak performance of 12 teraflop per second and cost $110 million back in 2001, so really, really expensive. So what we have at SDSC has 2.8 petaflop per second aggregate performance. So that's the performance that we get out of all our CPU cores and all the GPUs that are installed. We have 36 nodes that have each 2 NVIDIA K80 GPUs. And we have 36 nodes that have each 4 NVIDIA P100 GPUs. So each of those nodes has a performance of 5.5 teraflops double precision or 16.4 teraflops single precision. So you can see that a single node, at least of the K80 nodes, already has a higher performance in single precision than the entire ASCII White machine. And the P100s or 4 P100s outperform the entire ASCII byte machine already on with double precision. And in this case, the cost for the entire machine is $25 million approximately, where 14 million went into hardware and the rest is operation costs. Now, if you want to build your own supercomputer effectively, something that outperforms, at least in single precision, a supercomputer from 2 decades ago, you can go just online and you buy 4 NVIDIA RTX 2080 GPUs. These are some of the latest GPUs that are available, and you get a performance of 1.3 teraflops single precision, so that's 10% of the entire supercomputer ASCII byte back then, or you can outperform that significantly with 40 teraflops in single precision, and that costs you approximately $5,000, so you have a lot of computing power available by using GPUs. There is a lot.
There's a question.
Okay. So there's a question, is quad precision calculations possible on GPUs? If not now, anytime in the near future. So quad precision is not supported in hardware. So what you would have to do is you would have to implement that in software and make sure that it executes efficiently on the GPUs. So that's all I know about. Available nowadays, literally, virtually from any field. You can go from chemistry, life sciences, bioinformatics, so the astrophysics, so standard sciences, of course, also then finance, medical imaging, natural language processing, social sciences, weather and climate codes, fluid dynamics, and of course, machine learning, lots of machine learning lately. If you go to that link up there, NVIDIA has a very nice compilation of software that they support on their hardware, that they have supported developing, and with performance examples. So in general, it's actually a very nice idea to look around on their webpage because they have a lot of useful information up there. That's not only marketing. You have to take everything with a little bit of grain of salt. Of course, there is some marketing involved, but they have a lot of background in programming examples and so on. I'll tell more about that in a minute. Yeah, machine learning. So why is machine learning so popular in GPUs, or has such a big buzz on GPUs? And GPUs basically is driving a lot of the sales of GPUs. And so what you do in machine learning, so if you're not familiar with that, is effectively you're building predictive models based on reference data. So you have like training data that you train in a machine learning algorithm to build a model that then can be used with input data to make a prediction. And so you can check whether the predictions are accurate and then improve your training model. So that's basically very simplified the workflow that you typically take with machine learning. This is not a machine learning webinar, so I'm not going to talk much about it. But it's a big field. There are many different methods and algorithms, and what GPUs really shine at are deep learning workloads. And deep learning basically are neural networks with many hidden layers, as exemplified here on the bottom right. So you have an input layer, and then many of these hidden layers, and then an output layer. And effectively what that is tensor operations, which means a lot of matrix multiplications, and GPUs are very efficient at these. And if you go back and thinking about where GPUs come from, they were very good already like 10, 15, 20 years ago in doing 4x4 matrix algebra, because that's used in 3D graphics for rotations and translations and scaling of objects to compute the value of pixels on the screen. And then in addition to that, there's half precision arithmetic hardware that can be used for many machine learning applications, at least at the inference step, so at the prediction step. And if you go out and look at the machine learning frameworks that are available, for instance, like PyTorch or TensorFlow, these all provide GPU support. So you don't need to know much about GPUs. You basically need to tell that framework just, well, I want you to execute on the GPUs, and they will do that for you. So you don't really have to program and know a lot about GPUs in order to use those. Few benchmarks examples, right? So just a short comic strip, right? So you know that the Dilbert comics, and the question is, manager asks, do you have the benchmark results? And Dilbert says, do you want the 10-minute explanation of why the data are useless, or a simple here you go? He says, I'm in sales, well, here you go. So you have to be careful with benchmarks, because often people show benchmarks that show a certain performance increase of 100x of a GPU over some single-threaded core. So either they show it against single threads, or they show it against a non-optimized code, and that's of course not a fair comparison. So if you go back to some of the earlier slides that I showed, what is the performance differential on paper in memory bandwidth and floating point operations for GPU, then you can approximately estimate what is the maximum speed up that you could get, and that realistically should be somewhere around 10 at most, in comparison to say a dual core, a dual CPU socket. And there are many benchmark examples. I'll just show you two from my background, because I'm a quantum chemist and work in computational chemistry. So that's actually the main research that I'm doing is computational chemistry and molecular dynamics. But here's an example of a quantum chemistry code that basically is able to compute molecular properties from quantum mechanics, and a comparison of, for different types of molecules, you can see that you can get a significant speed up again here versus a reference code that is a different code that doesn't necessarily excel on single core performance, but the comparisons against a single core. In any case, it's a very fast quantum chemistry code. Also, molecular dynamics is very successful. That we have a very successful implementation for GPUs. So what we do, for instance, is atomistic simulations of condensed phase biomolecular systems. And what we need to do is we can need to compute the forces of all the particles that interact many, many millions of times to propagate the dynamics of the system. And this is an example of the AMBER molecular dynamics software package, and one of the latest benchmarks that you can see of a versus the CPU implementation that we have. So you can see the performance of a this year, for instance, a 36 core CPU implementation gets a performance of 2.35. That's the amount of simulation that we can get within 24 hours in a day. And already on gaming GPUs, you get a factor of 10 more with the implementation that we have. So if the code is implemented properly, you can get a significant speed up performance improvement. And that said, you know, this was a lot of work, so we'll get back to that. So it's not something that happens automatically necessarily. What's the catch, right? Again, another Dilbert comic. So our servers are using too much electricity. We need to use GPUs, right? We've seen that we get much more performance with much less power. And the manager says, I did my part by reading about GPUs in a trade journal. Now you do the software part. And after a while, he comes back and asks, why is your part taking so long, right? So it's not necessarily easy. But I'll show you what is involved in GPU programming. And then we can decide for yourself with your own projects whether you want to move forward with GPUs or not. So just as a very broad overview, a GPU versus CPU architecture, if you take the real estate of a integrated chip surface area, in a CPU, there are few processing cores, right? Arithmetic logical units, ALUs, but with sophisticated hardware. What's implemented is multi-level caching, prefetching, branch prediction. So the CPU does a lot in order to speed up the code that you have written. The GPU, on the other hand, has thousands of more simplistic compute cores, in a sense, that are packaged actually into a few multiprocessors. So they are physically arranged into multiprocessors. We'll see a little bit more about that later. And these operate at least partially in lockstep, right? So they are not they do not fully execute independently, and so you have to program that way. But it can have vectorized loads and stores to memory, and you need to manage the memory hierarchy. This has not changed much. So here you see a little bit of more details. That's actually from approximately 10 years ago, an NVIDIA GPU architecture, server with an early data center GPU. The basic architecture is still the same, and what you see here is SM is a so-called multiprocessor, which contains these processing cores that operate in lockstep. It contains also double precision compute core. So often the performance ratio of single precision to double precision is not 2:1 like on a CPU, in particular for gaming GPUs. Then there are special function units for special math operations that you might want to do. So not all the operations execute with the same performance, of course. There's an instruction cache, and then there's shared memory data cache that's shared across the processing units on these individual multiprocessors, but not across multiprocessors. And these streaming multiprocessors can handle many more threads than processing cores. So what you typically do is you launch many threads. So like it's written up here, you can launch in that old hardware configuration 128 threads per processor. And if you would do that, you would be having 30,720 threads running concurrently on that hardware. It doesn't mean they execute exactly at the same time, but they will be running at the same time. Then, there are certain hardware complexities because hardware characteristics have been changing across GPU models and generations. You still will write your code in such a way that it is portable and does not depend on the hardware, but you need to keep in mind that the single precision to double precision floating point performance ratio has been changing along the way. Memory bandwidth is different for different GPUs, GPU types. The number of compute cores and multiprocessors has been changing. The number of threads that the hardware can execute, the number of registers on a multiprocessor, and the cache sizes, and also the available GPU memory on the device, because the GPU memory is fixed, and you can't just add more memory. And so if you have applications that need a lot of RAM, they might actually not fit onto the GPU. The memory hierarchy needs to be explicitly managed. There's different types of memory. You have to know that there is CPU, of course, your CPU memory. Then on the GPU, you have different types of memory. That's global memory, shared memory that's sitting on the multiprocessors. There's texture memory and constant memory. And there's something called unified memory in CUDA, at least, that allows you to allocate memory. And then the CUDA toolkit, the runtime, takes care of automatically shuffling the data forth and back. But you still have to know that that shuffling happens, because the memory hierarchy still exists, and it will impact the performance of your code. So typically that's a good way to get started, but down the road you should explicitly manage the memory yourself in order to get performance. Then there are of course different hardware vendors. I've been talking a lot about NVIDIA because we do have NVIDIA GPUs at SDSC, and almost all data centers who are running GPU workloads are working with NVIDIA GPUs, but there's also AMD GPUs, of course, and they work differently in some ways. Here's a summary of different GPU models. The so-called compute capability determines the features that are available on NVIDIA GPUs. For instance, double precision support was introduced in version 1.3, but that's a long time ago, so all current cards support double precision, and that's here just an overview that you can pull information also from Wikipedia or from websites, NVIDIA's websites. What does that all mean for your program? So you should never write a code with any assumption of how many threads it will use. So, but similar to a CPU code where you will check how many CPU cores you have available, and then, for instance, an OpenMP code, you execute it with the number of threads that is equivalent to the number of available CPU cores. So you will use CUDA calls, CUDA functions to query the hardware configuration at runtime, and then launch many more threads than processing cores, but based on the type of hardware that you have. And what you also can do in order to improve performance is avoid using double precision when you don't specifically need it. So you have to be careful, because many algorithms, in particular scientific computing, are very sensitive to numerical precision. So you can't just switch double precision to single precision. But if you're careful, perhaps you can do some of your computations in single precision, and then, for instance, summations in double precision. And that's, for instance, what we're doing in a simplified explanation now, also in the AMBER molecular dynamics code. So if you want to program GPUs, there are different ways to do that. There's OpenCL, that stands for Open Compute Language. That's an industry standard, and it works both for NVIDIA and AMD GPUs, also for other devices. I'm not going to talk about that. There's CUDA, which is proprietary from NVIDIA, but it's freely available, and it's not going to go away anytime soon, and it's the de facto standard for high performance code on NVIDIA GPUs. Of course, it's going to run only on NVIDIA GPUs, so that's the downside. Then there's OpenACC. These are accelerator directives that do work both for NVIDIA and AMD. However, I'll talk a little bit more about that later. The implementations are not necessarily very efficient for both hardware types or render types, but it works with C, C++, and Fortran. So you would have a portable code that's similar to OpenMP. Now, OpenMP also has introduced accelerator and vectorization directives. That works well with Intel Xeon Phi and AVX512 vector extensions on CPUs, but is not made sure at the moment for GPUs, I would say. So it's not something that's recommended at the moment if you want to develop a production code to run on GPUs. Here's an overview of what I would call the NVIDIA GPU computing universe. So this overview basically has is just taken from the CUDA-C programming guide. So that's also a very good resource to look at. If you want to learn more about GPU programming, you can just read the programming guide that's online. So what NVIDIA provides is libraries like QDNN for deep neural networks, QFFT for fast Fourier transforms, QBLAST, that's a CUDA BLAST implementation, and so on. So there's many libraries, then there's programming languages. So you can use, you can program GPUs in CUDA from C, C++, and Fortran. There are also ways to use GPUs from Java and Python, or you can use a directive-based programming, for instance, like OpenACC. And then here's an overview of all the different types of GPUs that NVIDIA currently is supporting. So in principle, if you write a GPU code also in CUDA or with any of the other methods, directive-based programming, OpenACC is going to run on embedded devices, consumer desktops, laptops, professional workstations, and data center GPUs. So in that sense, the code is, of course, portable. What you have to know about is the CUDA toolkit. You can obtain that for free from NVIDIA at this link here. It contains the CUDA compiler, so NVIDIA NVCC. It also contains development tools. So there's a debugger, there's profilers. In particular, NVVP is a visual profiler. It's very nice and easy to use and gives you an overview of what's happening during code execution. There's also an IDE for Eclipse and Visual Studio, and a range of different libraries that I just mentioned on the slide before. And very importantly, there are also CUDA code samples that we'll have a quick look at later. So these are very nice to actually just get started a little bit and look at how CUDA programs can be written. So let's look at how to program GPUs. So there's basically three ways to use GPUs. So you have an application, and either you can use libraries. That's basically what we call a drop-in acceleration, right? So you have a function call to a standard library, and there's a CUDA implementation, so you can effectively just switch that in with a little bit of workaround in order to initialize the GPU, for instance. Then the next intermediate, say, difficult part is, so if you have part of your code that's compute intensive and you need to accelerate or want to run on a GPU, and it's not just a library function call, you can use directives and add those to your code. We will look at that at the end of this webinar. And then there are programming languages that give you, of course, the maximum flexibility to explicitly program using GPUs. So GPU accelerated libraries, of course, they're easy to use. So you don't need to know much about GPU programming. There's minimal code changes required. And of course, these are high quality implementations of functions that are encountered in a broad range of applications. And these have been tuned by experts, software engineers that have been put a lot of effort into that. So there's no way you can beat that usually. So if you use them, if you can, for instance, don't write your own matrix multiplication or fast Fourier transform functions unless you want to learn more about how to program, and that could be a simple example, for instance, to program matrix multiplication, and I have an example later that I'm going to show you. But don't use those in your own code. So if you go to NVIDIA's website here, so there's an overview of all the libraries. So there's deep learning libraries, there's linear algebra and math libraries available, there's image and video processing libraries, other libraries for other parallel algorithms, like for graph computations, for instance, and a lot of other libraries available by other partners that have been contributing to the GPU universe. So here's an example. So how to use libraries? There's basically 3 steps, right? So imagine you have a function call here, step 1, that is a function called saxp. That's a single precision a times x plus y. That's a so-called BLAS function, linear algebra function. And you just would replace that with a function call to qBLAS saxp, okay? You also need to manage what is called data locality. So basically, we'll look at this later with CUDA. You can allocate and copy data from the CPU to the GPU memory with CUDA malloc and CUDA memcopy. That corresponds to C malloc and C memcopy, if you're familiar with C. Or in Fortran, it would be basically an allocate and just copying data, right, from one array to another array. Now, if you use qBLAS, there are certain functions that you have to use for, or can use, for instance, qBLAS set vector and qBLAS get vector. And that's basically it. And then you rebuild and link the CUDA accelerated library. So you have to use the NVCC compiler and link it against the qBLAS library. And that's basically what's involved in using GPU accelerated libraries usually. So here's an example for that saxpy function. So we are doing a call to the saxp function, where now I have n elements and a, so this is the factor of 2, that's going to multiply x, which is dx, and y, which is dy, and the stride is 1 for this function. So it's called dx and dy now here. That's typically CUDA programmers use that in order to distinguish variables that are allocated in memory on the CPU and on a GPU, and then D for device. So that would be data that is available on the GPU. So what I would do here is I call the qBLAS saxp function. I have to pass it a so-called handle that I create by initializing the library. So that does some memory management for qBLAS. And then I have to shut down qBLAS at the end. I allocate the device vectors. So these are these memory arrays here, dx and dy, on the GPU. So that's the CUDA malloc function. And then I use the qBLAS set vector function to copy the vector x and the vector y to the corresponding array that's sitting on the GPU. So I transfer the data to the GPU, and at the end I read it back from the GPU. And that's basically how usually CUDA codes work. So you have data on the CPU, you transfer it to the GPU, then you execute your code on the GPU, and then you transfer the results back. Now, that's all I want to tell about libraries, because you know, if you want to use some of the other libraries, you just look into this manuals and see how they can be used. But now let's talk about CUDA. So CUDA is available again here from this link here, and we have CUDA C, which is a solution basically to run C code seamlessly on GPUs. It's available only for NVIDIA GPUs, but it is the de facto standard for high performance code on NVIDIA GPUs. It's NVIDIA proprietary, so it will not run on AMD GPUs or Intel GPUs, embedded GPUs. And CUDA C basically has a handful of extensions that you use with regular C code. So if you're familiar with C, it's not an issue to write CUDA code, but it still requires major rewriting of the code, because you have to think about how you want all the different threads to work on the data that you need to work on. The CUDA toolkit is free. I already talked about that, and it comes with a compiler, the math libraries, debugging and profiling tools, and there's also something called CUDA Fortran. So if you're a Fortran programmer, there are CUDA extensions in Fortran that have been developed by the Portland group, PGI. They're available in the PGI Fortran compiler, and PGI is now part of NVIDIA. So again, you know, extensions that used to work for AMD and NVIDIA GPUs work only for NVIDIA GPUs now. If you want to get started, these are 2 books that are actually good to have a look at, CUDA by Example and Programming Massively Parallel Processors. And of course, you can look at the CUDA programming guide, which is quite helpful. So how does a GPU program work typically? So people talk about heterogeneous computing. What that means is, it's not homogeneous. You just don't have just a CPU, but you have a CPU and a GPU, and the CPU is often referred to as host and the GPU as device. And so you would have, for instance, a C program that executes serially on the host, and at some point you hit a region of your code that then is executed on the device. Here exemplified by many threads here that are grouped into so-called blocks on a grid by calling something that's a kernel, that's a function that executes on the GPU. And when that is done, you can go back to your host. You have another part of your code that executes serially, does, for instance, some IO operations, and then you have another section of the code that executes in parallel on the GPU. So that's the general workflow of a GPU program. Now, if you think about what I said is the host and the device, so in the host you have a CPU and your GPU, CPU memory that you would normally program in a C or Fortran program, or well, any other programming language for that matter. And then typically connected by the PCI bus, you have the device, which is the GPU, that contains all these multiprocessors, each of which has many compute cores, some cache that's sitting between the RAM and the GPUs and the RAM that you can access on the device. So what you would do is to copy input data from the CPU memory to the GPU memory. Then you load your GPU program and execute it, caching the data on the chip for performance, ideally. We'll get to that in a little bit. And when you're done, you copy the results back from GPU memory to CPU memory. And what we have to keep in mind that this data transfer between CPU and GPU is slow, comparatively slow, because of the PCI Express bus limited memory bandwidth, and that can be a significant performance bottleneck. There is something that's called unified memory, and I mentioned before, you don't have to explicitly manage the memory. So what we looked at just on the slides before is, you have basically your system memory, the CPU memory, and the GPU memory, and you manage transfer between CPU and GPU memory. And if you use so-called unified memory, you don't have to worry about that. That's basically a pool of managed memory that is shared between the host and the device, and the CUDA runtime is automatically shuffling data forth and back whenever it needs to execute code on the GPU or transfer it back to the CPU to do some operations on the CPU. The memory copies, of course, still happen under the hood. And so you have to, it's a good idea to know that this still happens. And in order to optimize the performance, you might have to explicitly manage the memory yourself. I'll talk about some CUDA basics now. This is only going to be a few slides, so don't worry if you don't understand everything. It's impossible to, put everything into a short webinar, but I hope it's giving you a little bit of a background and a little bit of maybe a start to start digging a little bit deeper. So common terms that we hear about is a kernel, and in CUDA, a kernel is code, so typically a function that can be executed on the GPU, and the kernel code operates in lockstep on the multiprocessors of the GPU. And so these are executed and operate in parallel in so-called warps that currently consist of 32 threads. So the size of a warp is not guaranteed, but it has been 32 throughout the history of GPUs so far, NVIDIA GPUs. A thread is an execution unit of a kernel that has a given index attached to it to identify each thread. And each thread uses this index or can use these indices to access a subset of data to operate on. Threads are grouped into blocks. Blocks are guaranteed to execute on the same multiprocessor, which means that threads within a block can synchronize and they can share data via a shared memory that's sitting on that multiprocessor. And then the so-called grid is basically the total number of blocks that are executing on the GPU at the same time. And the total number of running threads, of course, is the number of threads per blocks times the number of blocks that are launched on the GPU to execute in parallel at the same time. So we see that exemplified here on the right. We have threads, blocks, grids, and warps. So the grid is the entirety of all our threads that are running on the GPU. They map onto a single GPU. So one grid is executing on the GPU. And it consists of multiple blocks. The blocks map to the multiprocessors. And blocks are never split across multiprocessors. But they can execute simultaneously on a multiprocessor. So you can have many blocks running at the same time on a multiprocessor. They don't necessarily execute at the same time. And then the threads are executed on the GPU cores and in groups of 32 executing in block steps. So what that means, if you launch a block of threads, you will always want to have a multiple of 32, so you don't have any threads that are sitting idle and doing no ops. There are built-in variables in order to control your code. And you can use those to compute the ID of each individual thread that is executing in a grid block. So you have block indices that give you the dimension of the grid, griddim.x, y, and z, and then block ID, so for the ID of the block. And so these variables return the grid dimension and the block ID in the x, y, and z axis. So you can have multi-dimensional blocks that can make it easier to map onto certain problems that you have. For instance, if you're operating on a vector, you might only want to use a single dimension. If you operate on a matrix, you might want to use two dimensions to make indexing easier. And then you have individual thread indices that give you the size of the blocks, so the block dim.x, y, and z, and the thread ID within a given block. And for instance, an example on the right here, we would have a grid that consists of 3 by 2 blocks, right? So we have 6 blocks running, and each block consists of 4 by 3 threads. So that means we would have 12 threads per block times 6 blocks, a total of 72 threads running in this example. Then if you write a function that should execute on the GPU, you use the __global__ keyword, and that designates a function that executes on the GPU. It must return void, but it is callable from the host code. You also can write functions that are callable from the GPU. For instance, here is a vector addition kernel that takes 3 pointers in, A, B, and C. And what we do is we have C as a result that it's the sum of A plus B. And the total size, we're passing in the size of the array. And so what we do is we compute a thread ID based on the thread ID of the currently executing kernel. So as you know, so each thread knows its thread ID and the block dimension and the block ID. And here we compute an offset based on the total number of threads in a block, which is the block dimension times the block ID. And this is the stride that we want to use to walk through the arrays. And so basically what we do, as long as our thread ID is less than the total size of the vector, we do that addition, right? So in each of the threads that is launched at the same time, there's an addition on a different element based on the thread ID, and that's how you write a parallel code on GPUs. The CUDA API also handles the device memory. I talked before about CUDA malloc, CUDA free, and CUDA memcopy, which is an equivalent of the memory allocation copy and functions of C. And so CUDA memcopy is used to transfer the data between the CPU and the GPU memory. And then finally, once you've written a kernel, you also have to launch the kernel, and you have to tell the GPU how many threads you want to run. And that's used with the kernel launch specification. So you use a triple angle bracket here when you're calling the vector addition kernel here with this triple angle bracket notation. And you give it the number of blocks, right? And you give it the number of threads in a so-called, there's a DIM3 data type basically that just contains 3 integers that default to 1. So if you don't specify by and bz, only dx would explicitly get a number that's different from 1. And the same for the number of threads. So here you would launch a grid of a certain number of blocks, and here you define the number of block size, and so that determines the number of threads that are running at the same time. So here's something about the memory hierarchy. I will try to go fast because we're already running a little bit late, and I wanted to show you also how to access Comet and Comet GPU nodes. But this is exactly what I've been talking about before. We have memory here that's sitting on the host. You have to transfer data to the GPU. On the GPU, you have something that's called global memory. That's visible to all threads, and access to that memory is slow. So what you want to use is so-called shared memory, but that's shared only within blocks that are guaranteed to execute on a given multiprocessor, because that's specific memory for each of the multiprocessors. So that shared memory is visible to all threads in a block, only within that block, but it's fast. And then you have registers, that's basically per thread memory. And you have something that's called local memory. That's a little bit confusing. It's actually not on that schematic here. That's actually, if you run out of registers, the data that your kernel that is executing requires to execute is going to store into local memory, which is thread private, but resides in global memory. So it's going to slow down your code. So what you want to do is you want to write code that doesn't spill out of registers. There's something called constant memory that can be very useful. It's visible to all threads. It's read-only from the GPU, so you can copy data there from the CPU. It's off-chip, so it's not on the multiprocessors, but it is cached. And importantly, it broadcasts to all threads in a so-called half-warp. So that can increase, significantly increase memory bandwidth if you have data that is used by many different threads at the same time. So given that memory hierarchy, so the general CUDA programming strategy is to avoid data transfers between CPU and GPU as far as possible, because these are slow due to low PCI Express bus bandwidth. Minimize access to global memory. So we would hide in our kernel's memory access latency by launching many threads, and take advantage of the fast shared memory that's sitting on the multiprocessors by tiling data. So we would partition data into subsets that fit into the shared memory, then handle each data subset within a given thread block, load the subset of data from global to shared memory using multiple threads. So you can exploit parallelism in the memory access, and then perform computations only on the data subset in shared memory. And each thread in a thread block can access that data multiple times, of course. And then once you're done, you copy the results back from the shared memory to the global memory. And at the very end of your program, of course, back to the CPU. There's an example that I have here about matrix multiplication. I think we are going to leave the slides on the available at our website. We'll post them on the training pages, so I won't go in detail through that. It's going to take too long to explain probably, but you know what you do is you allocate your memory on the CPU, on the device, you read in data from somewhere, then you copy the data that you have, so the matrix A and B from the device to from the host to the device, so CPU to GPU. You set your execution parameters, meaning the number of threads and the number of blocks in the grid, and then you call your kernel, in this case a matrix multiplication kernel. Now on the output data here that's sitting on the device, so the resulting matrix C, that's the product of A times B. And then when you're done, you copy that result matrix back from the device to the host, and you free your memory and you're done. And the way you want to do this is exemplified here. So this is actually taken from the CUDA C programming examples. If you look at that, you would see also a little bit of an explanation about that. But what you want to do is exactly what I was explaining. So you have a matrix multiplication of A times B, and the resulting matrix is C, and that's basically a lot of dot products. So vector dot products of rows by columns in matrix A and B. And what you would do is each block would copy a subset of the data into the shared memory, operate on that subset so that you don't have to access the data repeatedly from global memory, but you have it basically cached in the fast shared memory that you have explicitly managed to compute here the resulting matrix product. matrix elements of the product matrix. And then you move to the next block. And that's exemplified on the next 2 slides, but I'll just skip over this. You can have a look at that yourself. It's just showing on how you would do that if you would write your own matrix multiplication with optimization to use shared memory to minimize global memory access, latency, and bandwidth problems. But of course, you wouldn't do that, right? So we would, in this example, have used a few CUDA features, and that's very typical example of how you would write CUDA code. But in reality, for matrix multiplication, of course, we would just use the CUDA implementation of BLAS, which is highly optimized for GPUs. So I think that was the last slide about CUDA. And let me very quickly go over directive-based programming, just to show you some basics, and then have a quick look on how we can access GPUs on Comet and how we can compile code on Comet and execute GPU code on GPUs on Comet.
There's a question.
Yeah, so we have a question that, is there any LAPACK library for GPUs? There is, as far as I remember, so there's different options, and I personally don't have much experience with these libraries. There's some library that's called QLA that is partially free. I don't know if it's entirely free now, so you'd have to have a look at the NVIDIA websites. There is an effort that comes out of Jack Dongara's group that's called Magma, that actually works across different types of accelerators. And certainly it supports GPUs and multiple GPUs. And Magma is an implementation that, as far as I know, contains, it is stable and contains all functions that are available, or many of the functions that are available in LAPACK. So you would have to look about specifically the functions that you need, but I think there is a large code base available to you for use on GPUs for linear algebra that would replace LAPACK.
I pasted links to that.
Okay.
Good question.
So, directive-based programming. OpenACC is designed to make porting to GPUs easy, quick, and portable. It's an OpenMP-like compiler directives language. So if the compiler does not understand the directives, it will ignore them. It's just comments in the code. And so the same code, the ideas can be used to work with or without accelerators. In practice, that's not entirely true, but because you often have to think about and might have to restructure your code. But in principle, that is true. And it works for Fortran and C. It's fully supported by the PGI compilers that you can get for free from NVIDIA. Cray compilers and Crays, and there's a partial support by GNU compilers, and also some less commonly used and experimental compilers. So that's something that's moving forward. But in a few years from now, it might be that also OpenACC or functionality of OpenACC is basically merged into OpenMP. There are efforts along that direction, but it's not made sure at this moment, so we won't discuss this. So the PGI Community Edition is free. It contains the PGI compilers, Fortran C, C++ compilers, and has OpenACC support. It also contains the PGProf performance profiler and a handful of GPU-enabled libraries and some OpenACC code samples. So how to use it? So I talked earlier about a SAXP function, right? So you have an example here of SAXP, and that's an implementation of 8 times x plus y, and just a for loop, right? And all you do is you have insert a pragma here, ACC kernels, and that should automatically generate the corresponding GPU code and memory management and so on executed on the GPU. So in principle, it's really simple, right? And Fortran looks very similar. So you have a directive syntax where you have here in Fortran the $ACC directive or a pragma ACC and C, then the directive and some clauses. Often followed by structured code block. And for instance, if you look at the kernels construct that will generate kernels to be executed on the GPU, and then there are clauses if certain conditions, you can have if clauses or asynchronous execution, and then there are data clauses as well. What are data clauses? they are actually used to manage memory allocation. And that's what we've been talking about before with CUDA. You know, you have to know where your memory is living and what is happening. So there are different types of data clauses that you can use. And I'll show you an example. That is an example that comes, I think, from NVIDIA's websites as well, for Jacobi iterations that are used to iteratively converge to a final value. By computing new values at each point from the average of neighboring points if you have data on a grid, for instance, here. So Aij would be at time step or step k plus 1, computed as the average of the data from the resulting points on a grid, right? So you can use that, for instance, to solve the Laplace equation in 2D. And here's the code where you iterate until you're converged, right? So there's a while loop, so code in C here. Then you go across all the matrix elements J and I of your 2D grid in this case, and then you compute your resulting new values as the average of the neighboring values I plus 1, I minus 1, J minus 1, J plus 1, right? From the previous iteration. And then you compute the error as the difference of the matrix elements from before and with respect to the previous iteration. And you will stop if your error is below a certain threshold, right? Here in this while loop. And at the end, you need to swap the input and output arrays. Actually in C, also unfortunately, you could do that better just with pointers, but I mean, for just the purpose of this example, you would now copy the new results into the old results and then go to the next iteration of your loop. Now, okay, you could parallelize this on the GPU just by inserting Pragma ACC kernels and hope that it will execute on the GPU. So the compiler will generate code that executes in this part of the code on the GPU and then this part of the code on the GPU. And so, oops, this is actually the wrong command here. PGF90 is for Fortran code, but it's the same for PGCC is the C compiler. I would say that you want to accelerate the code. And minfo equals accel will give you some information about what the code is doing. So it's going to tell you, it's generating copy out and copy in. So that's data transfers. It will generate a kernel and has some information about the kernel. And if you run the code, so here's an example executed on SDSC Comet with the same code executing on a single thread or OpenMP parallel. So it doesn't scale very well, but you can see you get a speed of approximately 3 running on 6 cores. And if you use OpenACC, exactly the way that I've shown you in the slide before, it is terribly slow, right? So you get a slowdown and not a speed up. So something has gone wrong. Now, if we profile the code, and that can be done by setting like environment variable here, PGI ACC time equals 1. And execute the code again, we will see some information about what the code is doing. And there is here something device time, data copy in transfers, right? And data copy out transfers. So we have like here 22.5 seconds just data transfers, right? And then the compute is just 1.5 seconds down here, right? So you see the device time here for the kernel that's been launched. And what we have done is we spent all the time with data transfers between host and device effectively. And that's where we need to use those data clauses, right? Because what happens is these excessive data transfers in our code, we told OpenACC to generate these kernels, and it did that, and it realized, well, I need the data on the GPU in order to do these operations on the GPU. And at each iteration of the loop, it copies the data from the CPU to the GPU and then back from the GPU to the CPU. And that is, of course, not necessary. So what we do is we add data clauses here, and we're going to tell the code that, well, copy data, so A, that is the matrix A, to the GPU at the beginning of the loop. And it also implicitly means back out at the end. Create a new means allocate a new on the accelerator and just do no copies for a new, because that is used only on the accelerator. And if we do that, now you see that now we get the time down to 5 seconds, right? So that's significantly faster. That's a speed up of 4.8 versus the 6 OpenMP threads. So that's actually pretty reasonable. And I would say, you know, given the little work that was involved, is actually very, very nice result. There are more details about OpenACC because we are running late. I'm not going to talk much about that. You can have a look at that, but there are certain things that you have to be careful with your code. There are many pitfalls that, you know, you need to be aware of, that while the code is portable, you know, you must may have to restructure your code. For instance, functions with an accelerated regions must be inlineable, and so on and so forth. What's a good idea is to use the time option to learn where time is being spent in your code. And well, you have to eliminate pointer arithmetic, otherwise the code cannot automatically generate kernels, because it doesn't know what you're doing in memory. It's no guarantee. It doesn't have guarantees about memory being immutable. You should inline function calls. Use contiguous memory for multidimensional arrays. That's the same for CUDA and for OpenACC code. And then use data regions to avoid excessive memory transfers. And what you can also do is use a conditional compilation with the underscore OpenACC macro, depending whether you want to generate OpenACC code or not. I know that I'm at the end of my time, but I will now, I hope that, I apologize for people who have to leave. But it will be another maybe 10 minutes approximately. So if you have some time to spare, I would like to tell you on how to access the GPU nodes. If you have to run, I apologize. So just a quick overview, we have 36 older GPU nodes that have K80 GPUs. A K80 GPU has internally 2 GPUs. So really these are compute nodes with 4 GPUs. The nodes are 2 times 12 core Intel Xeon nodes that have these GPUs attached, and there's 12 GB of RAM per GPU. Then we have newer P100 GPU nodes, also 36 nodes with 4 P100 GPUs on each node. The configuration is very similar, but is a more modern GPU, Broadwell CPU here with 2 times 14 cores. The P100 GPUs have a little bit of more memory. They have 16 GB of RAM per GPU, and they're of course more efficient. So also when you use those, you get charged more as used, because I think it's a factor of 1.5 because the performance is higher. Actually, typically you get a factor of 2 out of many codes. So it could be beneficial to actually use those. If you want to know more, there is a user guide, of course, with all the information on the SDSC website. It's very simple. If you know how to log into Comet, you just log into Comet, and if you type qstat -q, you see the available queues. There are 2 queues for GPUs. One is called GPU. That's a queue where you would get entire GPU node with all the 4 GPUs, and there's a GPU shared queue where you can request individual GPUs. You can say, I want to use only a single GPU or 2 GPUs. Many codes will not run in parallel across multiple GPUs, so you often will just request a single GPU and do some sort of like ensemble simulations, for instance, that we do molecular dynamics, that we run many molecular dynamics simulations independently on individual GPUs. So the GPU nodes can be accessed by either the GPU or the GPU shared partitions. So if you have a job submission script, you would have sbatch command -p for partition, GPU or GPU shared. In addition to the partition name, which is required, you can also specify the type of GPU. That is optional. The type of GPU, and you can also, individual GPUs are scheduled as a resource. So you can have this dash, so minus gres equals GPU, and then you can specify the type and the numbers. So the GPUs will be allocated on a first available, first scheduled basis, unless you specify it with a type option. So if you don't say which type you're using, for instance, here gres equals GPU :4, you will get the first available GPU node, and that can be either K80 or a P100 node. If you want to make sure that you get a K80 node, you have to tell the sbatch command, or if you want to have a P100 node. In this case, you would request 4 GPUs, this example here. Yeah, so this is the example, and you would get the GPU partition and the P100, 4 P100 GPUs.
I also posted a link to the introduction to running jobs and comment where we have some GPU examples.
Yeah, so there have been GPU examples before also in some of the previous webinars on how to run jobs on Comet. If one thing that you should also know, and it's all documented, but I'll repeat it here, you should always set, if you use a shared GPU node, you should set the tasks per node, so the number of CPUs that you get per node equal to 6 times the number of GPUs if it is a K80 node, or 7 times the number of GPUs if it is a P100 node, because for each GPU there are 6, respectively 7 CPU cores, right? So here's an example on a GPU shared queue. You would choose 14 tasks when you request 2 P100 GPUs. There are also example job submission scripts and share apps examples GPU, and the charging is basically 1 SU for each K80 GPU hour and 1.5 SUs for each P100 GPU hours. If you want to use CUDA, you have to load the CUDA module. So you just say module load CUDA, that's it. And then the compiler will be available. So if you type nvcc -- version, you will get information about the CUDA compiler. There are different versions available. So by default, we have CUDA 7.0, but there's also newer versions if you require that for your code. The PGI module loads the PGIC and Fortran compilers. So for instance, module load PGI, and then here you could check the PGCC. Dash version is going to tell you should spit out the version of the PGI compiler that we have installed. Here's an example how you could get an interactive access to GPU nodes. That's basically using exactly the sbash commands that I have just been going over before. This is for interactive access. Very often it's hard to get interactive access on the GPU nodes because unless you have a specific reservation that you have requested, because there are just too many people running jobs on the GPUs, and we don't have a development queues for GPUs because there's so much in demand. You can use the NVIDIA system management and interface to get information about the GPUs. So if you type NVIDIA-SMI, you will get information about the GPUs that are installed. Here, for instance, an output that tells you, you know, you have Tesla P100 GPUs available. So there should be 4 showing up. Other jobs may already be running on the shared GPU nodes. So here's an example where, you know, NVIDIA SMI gives an output and says the GPU 1, 2, and 3 are running these jobs here, which in this case is a GPU accelerated version of a molecular dynamics program called PMEMD. The nodes of the shared GPUs, they are configured in such a way that the CUDA runtime only uses the requested number of GPUs, so you don't have to worry about doing that. So there's an environment variable that actually gets set. It's called CUDA visible devices, and that should be set to the GPU that is assigned to you, and you should not change that, but you can actually check it. In terms of CUDA programming examples, the CUDA toolkit, as I was mentioning earlier, comes with CUDA code samples, so you can install these, right? So you just execute this command, CUDA install samples, in this case, -7.0.sh. And the directory where you want to have that, and then it copies the code samples into this directory, in your home directory, for instance. And then you can explore these, right? So if I would move then into this directory, cd NVIDIA CUDA 7.0 samples, and do an ls, I would see like different subdirectories about like simple examples. There are some utilities, there are examples for graphics, imaging, and so on, and advanced examples. And there's a make file, so you can compile all of these just by typing make, and then execute those. So the compilation takes a while, and the executables will be in a subdirectory bin x86-64 Linux release. For instance, there's a tool that's called device query. If I go back on the previous slide, it's in this directory called 1_utilities, I believe. So you could also go directly there and compile that. And then if you execute this code, and you should have a look at it, because that's actually CUDA code that interrogates the GPU about features of the GPU. that in a way that you can also use in your own program. So if you execute this device query executable, it checks actually what capabilities the GPUs have that you currently have available. In this case example here, the output that you see means, it found one CUDA capable device, which means I was on a shared queue with requesting a single GPU, and it found a Tesla K80, and it's talking about the driver version, the runtime version, the CUDA capability, the memory that's available, the number of GPU CUDA cores, and so on and so forth. So all sorts of information that you could use for your, that might be useful for program execution and setting up on how to execute and launch kernels, the kernel configuration at launch time. There are many other examples. So for instance, the matrix multiplication example, you can have a look at that. That's in the also simple examples, 0_simple of the CUDA toolkit examples. And there is a basically hand-coded, optimized with shared memory matrix multiplication example. You can have a look at that to learn how that is programmed, in addition to the very simplified version that I have here on the slides. And you get a performance here, for instance, that's running on a Tesla K80 of 230 gigaflops. That's much less than the peak performance, right? So then if you use QBLAS, there's an example on how to use QBLAS. Now, if you look here, I'm executing the same. It's actually a slightly different matrix size. So it's not 100% fair comparison, but if you look at that, you get a performance of almost a teraflop, right? So yeah, use the libraries if you can. And that's the end. So I could show you interactively how to access the GPU nodes and look at the CUDA toolkit and compile sample OpenACC code, exactly that Laplace example. So I have that code available. We can post that on the, I believe, on the webinar.
The webinar page is where the intro is, but it'll take some time.
Yeah, so it will take some time, but we'll have that information available. So I'll stick around for a while if you have any questions. I apologize for taking longer than originally planned, but I hope.
Want to do interactive right now if anybody wants to hang around.
So if anybody wants to hang around, I'll stick around for a few minutes interactively if you have any questions. Thank you.
So I'm going to query and we'll just see who hangs around. Because there's still people who are dropping off.
Hi, Andreas. This is Dimitri.
Yes.
Hi, I have a question. Is it common that, how common is it that people use GPUs, one piece of code on GPUs, while at the same time running something on CPU, kind of overlapping?
This is actually a very common scenario. It requires a lot of load balancing and but also, for instance, the molecular dynamics codes, there are different approaches. That's something I can speak of from my own experience. The AMBER code executes entirely on the GPU, right? So everything has been rewritten for high performance on the GPU, and the CPU literally only does I/O, right? So you can attach a GPU to a very cheap CPU and the performance doesn't change. Other codes like NAMD or GROMACS, they have highly optimized kernels for CPU and for GPU, and they do part of the operations on the GPU. And so once a kernel is launched, the CPU doesn't have to wait until the kernel finishes, right? It can do work at the same time.
OpenMP threads for that?
You can use OpenMP threads, so you can use a threaded OpenMP code that runs at the same time as the GPU code. You just have to be careful, there are commands for synchronization so that, you don't have any race conditions in your code.
And do you think this such overlap can be efficient or?
It can be very efficient, yeah. So you can actually hide, memory transfer latencies with that, et cetera, et cetera. So it can be very efficient, but the one thing you have to know is that what you have to balance is, of course, in your hardware configuration, the performance of the GPU and the performance of the CPU, right? So if you execute part of your code on two different types of hardware, and you want to use those to the full extent, you have to make sure that you have a balanced hardware setup.
Okay, thank you.
We'll just wait a couple minutes and then
Mhm.
whenever you can set up and get started for that. This is great because then we can take that part of the video.
Okay, so, some people have some interest, I think, in quick demo.
Do you have your audio on?
Yes.
So let's have a quick look here.
So is Andy on now, audio? Are you, you're live now, Andy?
Yes, I'm live. Let me see if I can. Ooh. Can people see this? But no.
Yes. That's what I said.
Okay, so what do I have open here? Cancel. My shell is hidden under this. How do I move this?
Oh, just move the cursor down and it'll go away in just a second. It should.
No, it's been hanging around there all the time.
Oh, it has.
How can I move this? Oh, okay. Sorry. All right. So let's make this a little bit bigger. Okay, here's an example where I have logged into Comet already and I have accessed a GPU node. And let me just show you. So I executed the script here. Let me show you what's in that script. So that really is just an srun command where I had a reservation in place for this webinar, the reservation under this name. So that's something that you typically don't have. So I requested a GPU partition, so a node on the GPU partition, a single node with 28 tasks per node, so the entire node. And I requested a GPU P100 GPU, and I requested 4 of them, right? So in this case, time 2 hours. I guess I did that at, let's see, at 11, around 11. So there should be enough time available. Actually, also, if I'm looking at the job, it's still running. It's been running there in the background for 1 hour and 21 minutes. Okay, so let's.
A side question about how you can see what mathematical libraries that you can use with OpenACC. Do you want to do that later?
Yeah. So let's just keep going quickly here. The modules that I have loaded, these are just the default modules loaded when I log into Comet. If I want to use CUDA, I have to say module load CUDA. Of course, I can look at which are the modules that are available. And so here are the CUDA modules. So the default is 7.0, or if you want other versions, you can load the specific versions. Let's just load the default version, module load CUDA. It's available now. And if I type NVIDIA SMI, that's exactly what you see here are the 4 Tesla P100 GPUs. CUDA visible devices actually set to 0, 1, 2, and 3. So all the 4 GPUs are available to me. If I would have requested a shared compute node with only a single GPU, then only one of the devices would be visible to me, to the codes that execute on the GPUs. So let's have a look. What do I have here? I have the OpenACC examples here. The install. Oh, because when you want to show something, it doesn't work. I think there should be a command for installing the CUDA. CUDA home is here. So CUDA home shows you where the CUDA installation is. Have a look there. There is a bin directory. There should be, oh, it's called CUDA install samples. Okay. So the command was not install CUDA samples, it's CUDA install samples. So if I execute that CUDA -install samples 7.0, the current directory is going to copy the samples, for instance, to the current directory. So now I have the NVIDIA CUDA samples here. That's what I was showing you earlier. And if I go into this directory, there are different examples here. You can compile those just by typing make here, or you can also compile individual examples. That's what we're going to do now, for instance. I went into this directory 1_utilities, and it has different things like a bandwidth test and a device query, for instance. So let's have a look at this. Device query, there's a makefile, and there's the C++ source code. So if we have a quick look at the C++ source code, so there's a lot of like boilerplate, typically code in there by NVIDIA to catch errors and so on. But here it has a function that is CUDA get attribute, and so let's see what it's doing. It basically calls the QDevice get attribute function here. And here's the main program. So it's going to print some information about the device query is running and about the GPUs that are going that are in the system. So here, there's a CUDA device. This is part of the CUDA language, the CUDA device prop data type. And you can just call the variable device prop, and then it calls this CUDA device properties function, and then it's going to write information about the driver version, the runtime version, and all sorts of other properties that have been queried by this CUDA get device properties function, for instance, right? So you see here device prop dot, so it's this data type that contains, for instance, the total global memory, right, and the multiprocessor count and so on. So should be able to compile this. Let's compile the code. There's an executable here now, and if I call it, I will see a lot of information because I have 4 GPUs in the system actually, so it gets information for all the GPUs. And not surprisingly, on a P100 node, so it knows that device 0 is a Tesla P100, and the driver in the runtime version, so runtime is 7.0, that's what I have loaded. This is the capability version of the P100 GPU. It has 16 GB of RAM. It has, so let's see what information we have here. We have a total of 7,168 CUDA cores, right? So you already know if you launch CUDA code, you want to launch many more threads than there are cores. So you will launch like tens of thousands, hundreds of thousands of threads at the same time, which also means that the problems you're operating on should be sufficiently large, right? So if you have just a small matrix multiplication, it's not going to be very efficient on the GPU. So ideally, you're working, for instance, on larger matrix multiplications. The base clock frequency and so on, the L2 cache sizes, and there's some other information that is important, the shared memory per block, for instance, that you can use, the registers that are available to each block. The maximum threads that you can launch per multiprocessor. Somewhere there should be the number of multiprocessors. I don't see it currently. But basically you get all the information about, or much of the information about your GPU. And then there's 4 of them, device 1, 2, 3, and 4. And then there's some information whether you can have like peer-to-peer access between the GPUs and which GPUs, right? So between GPU 0 and 1, you have peer-to-peer access. That means, you can transfer data quickly across the GPUs. And between 2 and 3 and 1 and 0 forth and back, but so that has to do, but not between, for instance, GPU 2 and 0, because they're sitting on different, they are connected to the PCI Express bus that basically runs off the two different CPU cores. So that would be not possible. It's something that's called peer-to-peer access. So that's about device query, for instance, and then there are other examples like the simple examples here about the matrix multiplications. You could just look into their matrix tool, and it's the same thing. You can compile the code and execute it, and then you can have a look at the code and, as an example on how the code is written. So this already takes a little bit longer. Also, the makefile is written in such a way that it generates code for different compute architectures. We wouldn't have to do that because we have a P100 here, but the makefile is written such that it generates executable code that runs on the different hardware architectures. So in our case, we had compute capability 6. So there's actually no explicit code generated for compute capability 6.0, the lower one, 5.2. So that's probably the one code path that's going to execute when once the code executes on the P100 GPU. There's this matrix multiplication example, and there we go. So getting here a performance of 1.7 teraflops. I think we had 300 teraflops on the K80 for the same example, right? So this is significantly faster than the P100 GPU already with the simple matrix multiplication example. And if we go to the QBLAS example and we compile that, it compiles faster because it doesn't have to optimize and compile and generate code for the matrix multiplication itself, because it just links in effectively a call to the QBLAS library, and we execute that. Let's see. It should work. I haven't tested these things, so I don't know what's happening now. That's what always happens if you want to show something, it doesn't work. I'm not 100% sure what's happening here now. It should work. So I'm not able to tell you why it's not working. In principle, it should work. I have tested this earlier at K80 GPUs. It does work. So unfortunately, not able to tell you now. But I highly recommend looking at these code samples, and then I have these OpenACC samples that are exactly this Laplace 2D, the same way that you would do the module load PGI. And this Jacobi code is exactly the one that I was showing previously on the slides, and I have pre-compiled here an OpenMP version and a version that is optimized for the GPU. So for instance, if I do export OMP num threads, so that's for OpenMP equals 6, and I run the OpenMP version of the code, it's limited to 1,000 iterations. We'll see how long it takes. It takes, I don't know, something like 15, 20 seconds running on 6 threads. It's a little bit faster than what I have on the slides, because what I have on the slides I did on the K80 nodes that have older CPUs. So here it took 17 seconds. I think the other CPUs, the Haswell CPUs, takes around 20 seconds. And if I execute the GPU code, well, it's significantly faster. It's 10 times faster, right? So the P100s are actually very efficient, so much faster for this example than the K80 GPUs. So that's more or less what I wanted to show. I don't know if there are additional questions. I think there was a question about
OpenACC libraries and how to get more information.
So I highly recommend to go to the website, the documentation of both openacc.org. There's a lot of information, and then NVIDIA has for the PGI compiler also information. So let me see on my slides, for instance, if I go back to OpenACC, yeah, openacc.org, and here the OpenACC toolkit. There is information about additional resources, and you can find information. So I don't know details about the libraries for OpenACC, but all the information is here online, and also on openacc.org is quite a good resource.
Hi, Andreas.
Yes.
Do you know if do you know what is a good place to find examples of MPI programs using GPUs? Using MPI directly from GPUs.
That I actually don't know, for example. So most of the examples are simple. I mean, in the sense that, you know, it's focused on CUDA, but I mean, there are a lot of MPI programs, of course, with CUDA, and you can use MPI with CUDA. And so if you just Google for it, there must be information on NVIDIA's website. So Jeff Sale also said, so if you Google actually MPI, CUDA, GPU.
Yeah, we have examples.
So we have MPI solutions for GPUs, and there are also examples on Comet documentations.
It's very common.
So it's a very common setup to use MPI programs with CUDA and use multiple GPUs.
There's also CUDA aware MPI, and we have that in common.
Yeah. No more questions? Okay, so if there are no more questions, then I would like to thank all the participants for listening. And yeah, so the slides and I think the recording will be made available online later on the SDSC's webinar website. And so thank you very much. And I hope you will have fun with GPU computing and programming and make good use of our resources here at SDSC. Thank you.